Greetings, everyone. I'm Professor Lauren Chang from the Department of Space Science and Engineering at National Central University in Taiwan. Today, I'll be sharing some of our work in terms of developing spaceflight capacity and technology at our university, as well as building Taiwan's first university space center. So, at the moment, there are approximately 4,084 active satellites in Earth orbit, undergoing a variety of different types of missions. This reflects a growing trend of the utilization of space using small satellite platforms. This benefits development costs and development times, and also greatly reduces launch costs, and is expected to continue in the foreseeable future. However, there are several hazards in the space environment that can pose a threat to the operation of spacecraft, as well as space technology in general. The Earth's upper atmosphere extends to over 1,000 kilometers altitude. This portion of the atmosphere, called the thermosphere, can cause orbit perturbations through drag to Earth-orbiting spacecraft. This can cause their orbits to shift, and in severe cases can also cause spacecraft to deorbit. Additionally, the primary chemical constituent of the thermosphere is atomic oxygen, which is highly corrosive and can damage spacecraft structures and mechanisms. Additionally, we also are concerned of the photoionized portion of the Earth's upper atmosphere, which is called the ionosphere. Irregularities in ionospheric plasma can cause disruptions to satellite communications and navigation signals. Additionally, ionospheric plasma can also introduce a very significant range error to GPS and other global navigation satellite systems. This can reduce accuracy and can impede the development of autonomous vehicles that must rely on GPS for navigation. At National Central University, we have an extremely long history in space science and space technology. We were established in 1962 as a follow-on to the 1957-1958 International Geophysical Year, which saw the launch of humanity's first spacecraft for scientific exploration, Sputnik 1 from the Soviet Union and Explorer 1 from the United States. As a result of Taiwan's participation in IGY, NCU was established with a strong focus on the Earth and space sciences. Since then, in addition to space science and space physics, we've developed programs in space science and engineering, remote sensing, and astronomy. We've developed space technology, including scientific payloads, and this year we launched our first small satellite for a scientific mission. Our first satellite is called IdeaSat, which is short for Ionospheric Dynamics Explorer and Attitude Subsystem Satellite. IdeaSat is a 3-unit CubeSat. That is to say, its dimensions are 10 centimeters by 10 centimeters by 30 centimeters, so extremely compact and much cheaper to launch on a rideshare flight. The mass of the spacecraft is just 4.5 kilograms, again, making launch much more inexpensive compared to large satellites. The spacecraft is designed to function in a 500-kilometer sun-synchronous orbit, and the development of the spacecraft took place from between 2017 to 2020. The spacecraft was launched this January aboard a SpaceX Falcon 9 launch vehicle. Now, like any spacecraft, IdeaSat is a combination of multiple different subsystems which correspond to multiple different disciplines. In the case of IdeaSat, the subsystems of IdeaSat are a combination of both self-developed subsystems and also commercial off-the-shelf subsystems, which we then integrated, tested, and qualified for flight. Of the self-developed subsystems, this includes the UHF antenna, the spacecraft electrical power subsystem, the onboard computer, as well as the flight software that it runs, which allows the spacecraft to operate autonomously, as well as the 3U structure of the spacecraft. The maturity of technology can be measured using the technological readiness level, or TRL scale. At the moment, all of the subsystems of IdeaSat are either TRL 8 or TRL 9, which indicate that they have been launched and have operated in the space environment where their performance can be evaluated. We will continue to use the flight data that we have collected to improve our subsystems for use on future flights, as well as also potential commercial spin-offs. In addition to the spacecraft itself, we've also worked on developing the required supporting ground facilities to support mission command and control. This includes our ground station, which is used to track and communicate with spacecraft. Our ground station operates at 3 frequency bands, VHF, UHF, and S-band. We run signal processing as well as command and control software developed by our students that allow us to communicate with the spacecraft and also process the data that we've received from it. We've also built a Mission Operations Center at NCU that is used for tracking, communicating with our spacecraft, and also for educational purposes. These ground facilities continue to operate, tracking various small satellites, some of which we will be operating, and some of which our international partners are also operating. Now, our spacecraft was developed over the course of 3 years, starting in 2017. We started with mission concept and system definition, followed by the design phase. Like major spacecraft programs, we held preliminary and critical design reviews to ensure that our spacecraft design would be robust and would survive launch and function on orbit. Final fabrication, integration, and test phase for the spacecraft flight model took place from late 2019 through 2020, after which we conducted testing to qualify the spacecraft for launch. We delivered the fully qualified and tested spacecraft at the end of November 2020 to the launch provider, where it was then delivered to Cape Canaveral, Florida, to be integrated with the SpaceX Falcon 9. The launch vehicle was launched on January 24th of this year, and you can see from the pictures here the entire spacecraft development team in our department. Everyone is excited, but also very apprehensive. 4 hours after launch, the first flight data beacon packet transmitted by IdeaSat was received by an amateur radio ground station in Germany, demonstrating that the spacecraft had survived launch and had successfully powered on and begun operations. We found from the flight data received that the spacecraft was now operating successfully in safe mode. It had also successfully engaged in 3-axis attitude control. The spacecraft showed very good power margins with a very healthy battery state of charge of close to 95.28%. Over the course of the next month or so, we continued to autonomously track our spacecraft using our ground station, as well as ground stations of our partner institutions abroad, as well as the amateur radio community. We collected over 700 counts of flight data that were analyzed and demonstrated that the spacecraft was functioning stably, autonomously, and had engaged in several instances of autonomous error correction. Additionally, the spacecraft showed very good electrical, thermal, and link margins, demonstrating that the analysis work performed by our development team was robust. We did suffer a serious anomaly approximately 1 month after launch, when the spacecraft stopped communicating for close to a month and a half. The spacecraft recovered thereafter for enough time for us to uplink commands to the spacecraft, commanding the spacecraft to replay saved flight data that allowed us to determine the cause of this serious anomaly to a high level of confidence that we can fix on future missions. So, in conclusion, from the flight data that we received, the spacecraft demonstrated that it was capable of functioning on orbit and surviving launch with excellent margins in terms of power, communications, and thermal control. We also were able to demonstrate 3-axis attitude control, two-way communication, both uplink and downlink, and the return of flight data on orbit, allowing for the performance of the system to be evaluated. However, we found from our analysis that there are some modifications needed to the reset circuit in our self-developed electrical power subsystem, which is prone to single event latch-up due to radiation effects. The workmanship of our student team was verified to be very good. The spacecraft successfully survived the launch environment and activated and operated autonomously on orbit, providing a very unique experience for our students. So our self-developed avionics are now flight tested in TRL 8 to 9. We will continue to improve them using our accumulated flight data for future missions and also for potential commercial transfer. We are also performing work to improve the robustness of our self-developed avionics to allow for reliable operation for at least 1 year. Finally, through the execution of this mission, our students gained actual hands-on experience in spacecraft engineering, systems engineering, and also spacecraft operations, providing valuable training for Taiwan's next-generation aerospace workforce. IdeaSat is our first spacecraft, but we have more coming up, some developed by ourselves and some in collaboration with our international partners. We will continue to work building Taiwan's first university space center at NCU and continually providing unique educational opportunities for our students for hands-on experience in spaceflight. Thank you.